Introduction to Large Language Models, LLMs. Abstract. This article presents a study on large language models, LLMs, spotlighting their advancements post-ChatGPT's 2022 release. It emphasizes LLMs' proficiency in natural language tasks, attributed to extensive training on vast datasets, aligning with scaling laws. The paper aims to review notable LLMs, particularly focusing on the GPT, LLaMA, and PaLM families, analyzing their features, impacts, and limitations. Additionally, it explores the methodologies for constructing and enhancing LLMs, alongside evaluating popular datasets and metrics used in LLM training and assessment. A comparative analysis of LLM performance across various benchmarks is provided, aiming to highlight the strengths and weaknesses of each model. The conclusion addresses the challenges and future research directions in LLM development, aiming to outline the path forward in addressing computational efficiency, data bias, and ethical considerations in the continuous evolution of LLM technology. This summary encapsulates the paper's comprehensive examination of LLM's current state, contributions to NLP, and prospective areas for innovation. 1. Introduction: Large Language Models, LLMs, have not only emerged as a cornerstone in the advancement of artificial intelligence, AI, but have also ushered in a new era of natural language understanding and generation. Their transformative role in AI is profound, significantly expanding the capabilities of AI systems to perform an array of complex tasks. From basic text comprehension to intricate reasoning and creative text generation, LLMs have redefined the boundaries of human-machine communication. The advent of LLMs has revolutionized the interaction between humans and machines, enabling AI to understand and generate language with an unprecedented level of coherence and contextual relevance. This breakthrough has facilitated nuanced tasks, requiring deep comprehension of underlying concepts, emotions, and even humor, representing a significant evolution in AI technologies. Historical context and evolution. Language models have evolved from their inception, based on statistical methods that utilized probabilities to predict text sequences, to the adoption of machine learning and neural networks. This evolution marked a departure from rule-based systems to more sophisticated algorithms, capable of learning from vast datasets. Notably, the development of recurrent neural networks, RNNs, and the introduction of the transformer architecture have been pivotal, laying the groundwork for the development of current LLMs. Impact of ChatGPT and scaling laws. The launch of ChatGPT by OpenAI marks a significant milestone in popularizing LLMs, demonstrating their practical applications in engaging in human-like conversations, answering questions, and generating creative content. This era also underscored the importance of scaling laws in AI, revealing that increases in model size directly correlate with enhanced language understanding and generation capabilities, leading to notable performance breakthroughs. Capabilities of LLMs. LLMs are distinguished by their remarkable general-purpose abilities, excelling in in-context learning, where the model adapts to new tasks with minimal examples. Their capacity to follow complex instructions and perform multi-step reasoning as the model scales has opened new avenues for AI applications across various sectors, including customer service and creative writing. Emergent capabilities also arise as the model size increases, showcasing the potential for LLMs to handle increasingly complex tasks. Challenges and future directions. Despite the advancements, LLMs face challenges such as computational efficiency, data biases, and ethical considerations in their deployment. Future research is directed towards addressing these challenges, with a focus on enhancing model efficiency, mitigating biases, and aligning LLMs with ethical standards. Additionally, efforts are underway to improve the transparency and explainability of LLMs, aiming to make them more accessible and trustworthy for broader use. As we look towards the future, the impact of LLMs on technology and society is poised for significant growth. These models are expected to push the boundaries of AI capabilities further, reshaping our digital interactions and the landscape of AI applications. The ongoing evolution of LLMs highlights the dynamic nature of AI research and its potential to transform numerous aspects of our daily lives and work, heralding a future where AI and human intelligence converge more seamlessly. 2. Large language models, early pre-trained neural language models. The evolution of natural language processing, NLP, has been significantly shaped by the development of early pre-trained neural language models, NLMs, marking milestones in our quest to understand and generate human language through artificial intelligence. This journey, rich in innovation and discovery, has paved the way for the sophisticated language models we see today. Bengio et al. Early model. One of the foundational steps in this journey was taken by Bengio et al., who introduced a groundbreaking neural language model. This model tackled the pervasive issue of data sparsity, where rare words or phrases could derail the model's understanding by representing words as dense vectors. This approach allowed the model to grasp the semantics of words based on their context, laying a foundation for future developments in NLP. This model's significance cannot be overstated. It effectively bridged the gap between the raw text data and its numerical representation necessary for machine processing, enabling more nuanced language understanding and generation. RNNLM Toolkit by Mikolov. Mikolov's introduction of the RNNLM toolkit was another leap forward, utilizing recurrent neural networks, RNNs, to further the capabilities of NLMs. This toolkit made it easier for researchers and developers to apply NLMs to a variety of natural language applications, enhancing text generation and understanding significantly. Mikolov's contributions extended beyond this toolkit, making neural language models more accessible and influential, and highlighting the potential of RNNs in capturing sequential information for language tasks. The Transformer Revolution. The introduction of the Transformer architecture by Vaswani et al. Marked a revolutionary shift in how language models were designed. Transformers abandoned the sequential processing inherent to RNNs for a parallel approach, enabling drastically improved efficiency and model performance. This architecture's self-attention mechanism allowed each word to dynamically adjust its representation based on its context within a sentence, leading to a profound improvement in handling long-range dependencies and nuanced language understanding. Encoder-only PLMs, encoder-only pre-trained language models, PLMs, have revolutionized the field of natural language understanding, with seminal models like BERT, RoBERTa, ALBERT, deberta, XLM, xlnet, and UNILM leading the charge. Each model has contributed uniquely to advancing the capabilities of NLP systems. BERT, bidirectional encoder representations from transformers. BERT, bidirectional encoder representations from transformers, introduced a groundbreaking approach in NLP with its MLM, masked language model training strategy. By masking random words in a sentence, BERT learns to predict them using the context from both preceding and following words, enabling a deep understanding of language nuances. This bidirectional context comprehension allowed BERT to understand nuanced language patterns and significantly improve performance across a range of NLP tasks, including question answering and language inference. BERT is pre-trained using two objectives, MLM and next sentence prediction. Next sentence prediction significantly enhances performance across various NLP tasks, like question answering and language inference. Let's delve deeper into BERT's three main modules. 1. Embedding module. At its core, the embedding module transforms input text into a sequence of vectors. These vectors represent words in a high-dimensional space, capturing semantic and syntactic nuances. The process starts with tokenization, where text is broken down into manageable pieces, followed by the conversion of these tokens into embedding vectors. This module combines token embeddings with position embeddings to maintain the sequence order, a crucial aspect for understanding the context. 2. Stack of transformer encoders, the heart of BERT. This stack processes the embedding vectors to generate contextual representations. Each encoder in the stack comprises two main components, a multi-head self-attention mechanism and a position-wise, fully connected feed-forward network. The self-attention mechanism allows the model to weigh the importance of different words within the same sentence, facilitating a nuanced understanding of context and relationships between words. These encoders iteratively refine the embeddings, layer by layer, enriching them with broader contextual information. 3. Fully connected layer. The final piece of the puzzle. This layer takes the contextual representations from the last transformer encoder and transforms them for specific tasks. For the MLM objective, it predicts the original identity of the masked words, effectively turning BERT's deep contextual understanding into actionable predictions. When fine-tuning for downstream tasks, this layer can be customized or replaced to suit the task at hand, from classification layers for sentiment analysis to multiple choice layers for question answering. Together, these modules enable BERT to grasp the intricacies of language, setting a new standard for a wide range of applications in NLP. RoBERTa, robustly optimized BERT approach. RoBERTa, robustly optimized BERT approach, evolves from BERT, enhancing its pre-training methodology for better NLP outcomes. It tweaks crucial hyperparameters for efficiency, notably discards BERT's next sentence prediction task, considering it not as beneficial for model understanding. Deberta also amplifies the volume of data processed in each training step by increasing mini-batch sizes, coupled with a higher learning rate. This approach ensures more extensive and varied data exposure per update, significantly contributing to the model's learning depth. These strategic modifications not only boost Deberta's performance across various language tasks, but also reinforce its robustness, making it a formidable model in the realm of NLP, adept at capturing nuances in language with improved accuracy. Albert, a light BERT. Albert addressed BERT's scalability issues by introducing two key innovations: factorized embedding parameterization, which reduces the size of the word embedding matrix, and cross-layer parameter sharing, which decreases the number of independent parameters and thus the model's overall size. These modifications allowed Albert to achieve comparable or even superior performance to BERT with significantly fewer parameters, showcasing the potential for more efficient, large-scale NLP models. Deberta, decoding enhanced BERT with disentangled attention. Deberta, decoding enhanced BERT with disentangled attention, introduces advancements to the BERT and Deberta frameworks through unique mechanisms aimed at refining the understanding and representation of language. The first key innovation is the disentangled attention mechanism, which represents each word with two distinct vectors, one for the word's content and another for its position within the sentence. This allows the model to compute attention separately based on the semantic content of words and their relative positions, enhancing the model's ability to grasp the nuances of language structure and context. The second enhancement involves an improved mask decoder that integrates absolute positional information in the decoding process. This adjustment helps the model better predict the identity of masked tokens during pre-training, leveraging both the content and precise placement of words within a sequence for more accurate reconstruction of the original text. Furthermore, Deberta employs a novel virtual adversarial training technique during fine-tuning, which introduces small perturbations to the input data to make the model's predictions more robust to slight variations. This method enhances the model's generalization capabilities, allowing it to perform more consistently across different datasets and tasks. Together, these innovations make Deberta a powerful and efficient model for a wide range of natural language processing applications, building on the strengths of its predecessors while introducing significant improvements in attention mechanisms and training methodology. Electra introduces an innovative pre-training task called replaced token detection, RTD, enhancing the efficiency of learning compared to the masked language model, LLM, approach. Rather than merely masking words in the input, RTD actively corrupts it by substituting some tokens with plausible but incorrect alternatives generated by a smaller network. The crux of Electra's approach lies in training a discriminative model to discern whether each token in the corrupted input was the original or a replacement. This method covers the entire input, offering a broader learning scope than LLM, which only focuses on a limited number of masked tokens. This comprehensive analysis of all input tokens makes RTD notably more sample efficient. XLM Cross-Lingual Language Model. XLMs, cross-lingual language models, advance BERT's framework into the multilingual domain using two strategies: an unsupervised method that uses monolingual data from multiple languages, and a supervised method that utilizes parallel texts, the same content in two different languages. The supervised approach introduces a novel objective, making XLMs adept at understanding and translating languages by leveraging the context available in one language to inform the processing of another. This dual approach enabled XLMs to achieve top performance in tasks like cross-lingual classification and both unsupervised and supervised machine translation, showcasing their versatility and power in bridging language barriers in NLP applications. xlnet, an encoder-only language model, innovates by integrating Transformer XL's architecture with a novel pre-training strategy. Unlike traditional models that predict words in a fixed sequence, xlnet uses a generalized autoregressive approach, permuting the order of words in the input text. This method allows xlnet to consider every possible arrangement of words, effectively learning from bidirectional contexts without a predefined direction. This flexibility in capturing relationships between words enhances its understanding of language nuances, setting xlnet apart by enabling it to predict the context of a word based on all other words in a sentence, thereby improving its performance across diverse NLP tasks. UNILM, Unified Language Model. UNILM, Unified Pre-trained Language Model, stands out by integrating three distinct language modeling techniques: unidirectional, predicting the next word given the previous context; bidirectional, understanding words based on context from both sides; and sequence-to-sequence prediction, transforming an input sequence into an output sequence. It utilizes a unified transformer architecture, employing specialized self-attention masks that dictate the context each part of the model can access during training. This versatile setup allows UNILM to excel at a broad range of tasks, from understanding complex texts to generating coherent and contextually relevant language, by fine-tuning the pre-trained model for specific NLP tasks, whether they require understanding the text, generating new text, or both. These encoder-only PLMs have collectively pushed the boundaries of what's possible in NLP, each contributing unique insights and methodologies that enhance our understanding and processing of natural language. Through their advancements, they've laid the groundwork for future innovations in AI and language understanding. Decoder-only PLMs. The development of decoder-only models, such as GPT-1, GPT-2, GPT-3, GPT-4, shifted the focus towards text generation and highlights significant advancements in natural language processing. These autoregressive models generate text by predicting the next word in a sequence based on the preceding context, producing coherent and contextually relevant passages. The success of these models in generating narrative text highlighted the potential of NLP in creative and generative applications, and the journey from GPT-1 through GPT-4 showcases a progressive enhancement in understanding and generating human-like text, driven by sophisticated AI techniques. GPT-1 and the generative pre-training strategy. GPT-1, or Generative Pre-trained Transformer 1, is a pioneering model in natural language processing, NLP, that introduced a novel approach to understanding and generating human-like text. It operates on the transformer architecture, which is fundamentally based on the mechanism of self-attention. This allows GPT-1 to weigh the importance of different words within a sentence, enabling it to predict the context of a word based on all the other words around it, rather than relying on the sequential order. The core idea behind GPT-1 is twofold: pre-training followed by fine-tuning. During pre-training, GPT-1 is exposed to a massive corpus of unlabeled text data. Here, it learns to predict the next word in a sentence by treating each word as a blank to be filled, a process known as generative pre-training. This self-supervised learning method does not require explicit labels or annotations, allowing the model to learn a broad understanding of language patterns, syntax, and semantics autonomously. After pre-training, GPT-1 undergoes a phase of discriminative fine-tuning. In this stage, the model is further trained on a smaller, task-specific dataset. Unlike the pre-training phase, fine-tuning involves adjusting the model's parameters to perform specific NLP tasks, such as text classification, sentiment analysis, or question answering, with much fewer examples. This two-step process leverages the general language understanding developed during pre-training to adapt to particular tasks efficiently, demonstrating remarkable versatility and performance across a wide range of NLP applications. GPT-1's breakthrough lies in leveraging the transformer's self-attention mechanism for pre-training on extensive text data in a self-supervised manner, followed by task-specific fine-tuning. This methodology not only paved the way for subsequent advancements in the GPT series, but also set new standards for building versatile and powerful NLP models. GPT-2's architectural and training enhancements. GPT-2 expanded on GPT-1's architecture and training regimen, utilizing the web text corpus, a vast dataset derived from millions of web pages. This model introduced critical architectural improvements, such as moving layer normalization to the input of each subblock and adding an extra layer normalization after the final self-attention block. Layer normalization is a technique that stabilizes the distribution of non-linear inputs to a layer, enhancing training speed and stability. The self-attention mechanism, a hallmark of the transformer architecture, allows the model to weigh the importance of different words in a sentence, improving its understanding of context and relationships between words. By adjusting the initialization method and expanding the vocabulary and context window, GPT-2 could better generalize language understanding and generation, learning implicitly from its training data without direct task-specific instructions. GPT-3's generative pre-training and self-supervised learning, GPT-1 and GPT-2s, lay the foundation to more powerful modern LLMs, like GPT-3, which leverages a vast amount of text data for pre-training in a self-supervised manner, meaning it predicts the next word in a sentence without needing labeled data for this task. This form of learning allows the model to understand and generate human-like text by recognizing patterns, syntax, and semantics across diverse text samples. In context. Learning explained. In-context learning refers to GPT-3's ability to perform tasks it wasn't explicitly programmed to do. By providing a few examples, prompts, within the input text, GPT-3 can generate responses that adhere to the implied task rules, showcasing an understanding that goes beyond the specific content it was trained on. This feature simulates a form of quick adaptation akin to human learning, where a small amount of new information can significantly expand our ability to apply knowledge in novel situations. Emergent abilities. The term emergent abilities with GPT-3 signifies the model's capacity to exhibit behaviors or skills that were not directly taught during its training phase. These abilities emerge from the complex interactions within its vast network of parameters, enabled by the scale and depth of its architecture. Such capabilities include, but are not limited to, translating languages, writing coherent essays, solving puzzles, and even generating programming code based on the descriptions provided in natural language. In summary, GPT-3 represents a monumental step forward in machine learning, particularly in NLP. Its emergent capabilities, epitomized by in-context learning, demonstrate an unprecedented level of linguistic and cognitive flexibility, bridging the gap between human and machine understanding of language. This technology not only showcases the potential of scaling up model parameters, but also opens new avenues for AI applications across various domains without the need for extensive task-specific data or adjustments. GPT-4's multimodal capabilities. GPT-4 took a leap forward by incorporating multimodal capabilities, processing both text and images. This development meant that GPT-4 could understand and generate content that relied on visual as well as textual context, broadening the scope of applications for language models. Despite challenges in complex real-world scenarios, GPT-4 demonstrated near-human performance on various benchmarks, illustrating the potential of multimodal models in bridging the gap between human and machine understanding. The GPT series, through its innovative use of generative pre-training, self-supervised learning, and strategic enhancements in architecture and training methods, has significantly advanced the field of NLP, from GPT-1's foundational strategy to GPT-4's sophisticated multimodal capabilities. Each iteration has contributed to the deepening understanding of language and the expanding potential of AI applications. This journey underscores the transformative impact of decoder-only PLMs on natural language processing technology, setting new standards and opening new possibilities for AI-driven communication and analysis. Encoder-decoder PLMs. According to Raffel et al.'s paper, nearly every NLP task can be framed as sequence-to-sequence, seq-to-seq generation, making encoder-decoder models versatile for both understanding and generating language. These models work by encoding an input sequence into a dense representation, which the decoder then uses to generate an output sequence. This process allows the model to convert one form of text into another, applicable across various NLP tasks. In sequence-to-sequence, seq-to-seq tasks, the goal is to transform an input sequence, like a sentence in one language, into an output sequence, like a translation of the sentence in another language. T5, text-to-text transfer transformer. T5 redefines the approach to NLP using transfer learning in a unified framework, where all NLP tasks are treated as a text-to-text generation task. Whether it's translation, question answering, or classification, T5 treats inputs and outputs as strings of text. This simplification allows for a highly flexible model that can be applied to a broad range of tasks using a uniform approach. T5's pre-training involves corrupting text with a span masking technique, where consecutive words are replaced with a placeholder, and the model learns to predict the masked span. This method builds a deep understanding of context and language structure. MT5, Multilingual T5. MT5 builds on the T5 model, but takes it global, learning from texts in 101 languages collected from the internet. This means MT5 gets really good at understanding and talking in languages from all over the world, making it super useful for any task that involves language, like translating or creating new text. Just like T5 turns everything into a text-in, text-out problem, MT5 does the same, but in many languages. It's like having a polyglot friend who not only speaks lots of languages, but can also switch between them seamlessly, helping you understand or express anything from Spanish love poems to Japanese instructions. It's like a smart friend who not only speaks and writes in 101 languages, but can also mimic the way people talk in different parts of the world. It learned this by reading a huge library of texts from the internet, making it a jack-of-all-trades in languages. Mass masked sequence-to-sequence pre-training. MAS, masked sequence-to-sequence pre-training, utilizes the encoder-decoder architecture to enhance language understanding and generation. By masking a fragment of a sentence, the encoder processes the partial input, while the decoder works to predict the missing tokens. This method enables simultaneous training of both components, with the encoder learning context and the decoder focusing on generation. MAS's approach effectively bridges language embedding and generation tasks, preparing the model for a broad range of NLP applications by improving its grasp of context and its ability to reconstruct language. In other words, MAS is like a game where part of a sentence is hidden, and the computer has to guess what's missing. It splits the job in two. One part, the encoder, reads the sentence except for the hidden bit, and the other part, the decoder, tries to fill in the blank. By playing this game a lot, MAS gets better at understanding language and can help generate text, kind of like finishing sentences in a super advanced way. BART, bidirectional and autoregressive transformers. BART operates on a sequence-to-sequence model, akin to a translator translating from one language to another. However, instead of languages, BART translates corrupted text back to its original form. During pre-training, it deliberately messes up the text using various methods, like deleting words or jumbling sentences, and then trains itself to fix these alterations, restoring the text to its initial state. This process helps BART get really good at understanding context and the structure of language, making it versatile for tasks like summarizing articles or fixing grammar. In simpler terms, think of BART as a super smart editor. First, it scrambles a piece of writing, mixing up or hiding parts of it. Then it challenges itself to put everything back correctly, learning a lot about language in the process. It's like doing puzzles to get better at solving them. These encoder-decoder models leverage the transformer architecture's ability to handle long-range dependencies and understand the complex structure of natural language. By pre-training on massive text corpora and fine-tuning for specific tasks, they achieve remarkable performance across a wide spectrum of NLP challenges, demonstrating the flexibility and power of the encoder-decoder approach in modern language models. These advancements in early pre-trained neural language models set the stage for the current and future exploration of NLP, demonstrating the field's dynamic nature and its potential to transform how we interact with technology through language.